4.5 billion miles from Earth, in absolute darkness, the James Webb Space Telescope just found something that should not be there. Water ice where radiation should have destroyed it. Organic molecules more complex than cold space can produce. Objects moving in patterns that defy random chance. We are going inside the outermost edge of our solar system, past frozen worlds, through regions colder than anything on Earth, toward a discovery that is forcing scientists to rewrite the rules of how solar systems work. If you enjoy this journey, hit like and subscribe. It means more than you know. Take a breath. We launch into the deep. Most people picture our solar system as a neat disk, 8 planets circling a glowing star, everything clean and orderly, with a hard border at the end. That picture is wrong. The real edge is not a line. It is a gradual, shifting, invisible boundary where our star's influence slowly fades into the broader galaxy and stops completely. Think of it like a storm. At the center, the winds are fierce and constant. As you move outward, the gusts weaken. Eventually, far from the eye, the storm simply dissolves into calm air. You never step over a wall. The storm just runs out of power. Our solar system works exactly the same way. The star at our center constantly blasts outward, a stream of charged particles. Scientists call this the solar wind. This wind travels in all directions, reaching incredible speeds, and it pushes outward against the interstellar medium, the thin sea of gas and dust filling the space between star systems. For billions of miles, this solar wind dominates. It carves out a giant bubble of influence. Inside this bubble, our star's radiation shapes everything. Outside it, the galaxy takes over entirely. The boundary between these two regions has a name. Scientists call it the Heliopause. For most of human history, we had no idea what it actually looked or felt like. We only had models, guesses, simulations run on supercomputers in labs, far from the cold silence they were trying to describe. That changed in 2012, when Voyager 1 crossed it. What the probe reported was strange. The solar wind, weakening for decades, did not just slow down near the edge. It stopped almost completely. Then the probe detected a sudden spike in cosmic rays, high-energy particles blasting in from deep space, held back for billions of miles by our star's wind, now flooding in all at once. It was like walking through a door. One side, our star's breath. The other side, the galaxy breathing instead. But here is where things get interesting. Scientists assumed the edge would be smooth, symmetrical, a bubble. It is not. Recent data from multiple probes suggests the heliopause is lumpy, dented, irregular, almost like a comet's tail, pressed flat on one side by the galaxy's own wind and stretched long on the other. It is dynamic, pulsing slightly with every burst of solar activity from billions of miles away. And now, the James Webb Space Telescope has turned its gaze toward this region. Not just at the boundary itself, but at what lies just inside it, in a zone so far out that light from our star takes over 17 hours to reach it. What Webb found in that zone was not what anyone expected. The data came back in fragments at first, small inconsistencies, readings that did not match the models, objects where there should be nothing, signatures of materials that had no business being out there in the dark. Scientists ran the calibrations again. Then again, the readings held. Something was out there. And what lay beyond that edge will take your breath away. The instruments Webb uses can detect heat signatures so faint they border on the impossible to measure. In this outermost zone, where temperatures hover near the coldest point the universe allows, those instruments started picking up something that did not belong. Scientists ran the numbers 3 times before saying anything out loud. What they found would take months to fully understand. 2 small machines are drifting right now through the coldest, darkest territory in our solar system. No human built anything else that has travelled this far. They carry gold records with sounds from Earth, mathematical diagrams, greetings in dozens of languages. They were launched in 1977, and they are still sending back data. Voyager 1 crossed the Heliopause in 2012. Voyager 2 followed in 2018. The data they sent back in those moments changed our picture of the edge forever. For years leading up to the crossing, scientists watched the solar wind readings from both probes weaken. Slowly, gradually, the stream of particles washing over the probe since launch began to thin out. This was expected. The solar wind naturally loses energy over distance. But then something unexpected happened. The weakening was not gradual near the actual boundary. It was sudden. Solar wind readings dropped sharply over a very short distance, almost as if both probes hit a wall. On one side, solar particles. On the other side, almost none. At the same moment, cosmic ray counts jumped dramatically. These particles come from outside our solar system, from ancient supernovas and distant energetic events across the galaxy. For the entire journey, they had been mostly blocked by the solar wind bubble. The moment the probes crossed the heliopause, those particles flooded in. Voyager 1's plasma wave instrument detected something else. Vibrations. Actual oscillations in the surrounding medium. Scientists translated those oscillations into audio frequencies and released the recording. It sounds like a faint, eerie hum, a wave moving through thin, interstellar gas. Our solar system was ringing, faintly, from the outside. But what stunned researchers most was not the particles or the vibrations. It was the temperature. Just inside the heliopause, the solar wind is paradoxically very hot, despite being far from our star. The particles are moving fast, which translates to high temperature in physics terms. But just outside the boundary, the interstellar medium is far denser and cold in a different way. The transition happens over just a few 100 million miles. In space terms, that is almost nothing. Now imagine what the James Webb Space Telescope can see in this region, that a probe flying through it cannot. Webb does not fly through anything. It sits roughly 1 million miles from Earth and looks outward with the most sensitive infrared eye ever built. It detects the faint heat signatures and chemical traces of objects that probes will never reach in any of our lifetimes. When Webb looked at the outer edge of this boundary region, it picked up something the probes never could have found even flying directly past it. A shape, a structure, something that had been sitting silently in the dark for potentially billions of years. Before we reveal exactly what that object is, we need to travel through the zones between here and there, because the territory leading up to the edge is filled with its own secrets. And the next one is the boundary itself. And yet, here we are, two tiny machines, built decades ago with technology that would seem primitive today, are still our only eyewitnesses to what happens at the boundary. Every reading they send back takes hours to arrive, traveling at the speed of light across billions of miles. Scientists receive those readings, analyze them carefully, and compare them to what Webb now sees from afar. Together, the picture they build is unlike anything the models predicted. The heliopause is the most important boundary most people have never heard of. It is not a physical wall. You could pass through it without feeling a thing. There is no surface, no visible line, no dramatic flash of light, and yet it is the true border of our solar system. Everything inside it belongs to our star. Everything outside belongs to the galaxy. Our star does not just give off light. It constantly ejects matter. Every second, millions of tons of charged particles stream outward in every direction at speeds close to 1 million miles per hour. This is the solar wind. It does not slow down much for tens of billions of miles. It just keeps pushing, carving out a region of space dominated by our star's influence. But space is not empty. Between the star systems of the Milky Way, a thin mix of hydrogen, helium, and trace elements drifts slowly. Scientists call this the interstellar medium. It has its own pressure, its own slow movement, pushed around by the collective gravity and radiation of billions of stars. At some point, the outward pressure of our star's solar wind perfectly balances the inward pressure of the interstellar medium. That balance point is the heliopause. It is not a fixed location. It breathes. When our star has an unusually active period and throws off more particles, the heliopause expands slightly. When activity decreases, it contracts. Scientists estimate the heliopause sits roughly 11 billion miles from our star in most directions. To picture that, consider that light, the fastest thing in the universe, takes over 16 hours to travel that far. For decades, scientists assumed the solar wind bubble would be roughly spherical, balanced, like a soap bubble floating in still air. It is not. Data from multiple sources, including the probes and Webb's observations, suggests the heliopause is severely asymmetrical. On the side, facing the direction our solar system is moving through the galaxy, the boundary is compressed, flattened, pushed inward. On the opposite side, it stretches out into a long, comet-like tail billions of miles behind us. Our solar system is moving. Not just Earth orbiting our star. The entire system is hurtling through the Milky Way at roughly 450,000 miles per hour. As it moves, it pushes through the interstellar medium, the way a boat pushes through water. The heliopause is the bow. Webb detected something near this bow region. An elevated concentration of material in the zone just inside the heliopause, where the solar wind meets the interstellar medium, and both slow down before the actual boundary. Scientists call this zone the heliosheath. The material Webb found there had a specific spectral signature, a unique pattern of light absorption that astronomers can read like a fingerprint. It matched molecules that form under very specific conditions, cold, dark conditions, but also complex ones, more complex than random cosmic debris should produce. Something about this region was organizing chemistry in ways that current models do not explain, and the further inward Webb looked, the stranger the picture became. That is the deeper implication of Webb's observation near the heliosheath. If chemistry can organize in this transitional zone, if molecules can become more complex in the very region where two vast forces meet, then the boundary of our solar system is not just a physical edge. It is a chemical one too. A place where one kind of chemistry ends and another, stranger kind, begins. For most of the 20th century, scientists treated the outer solar system as a graveyard. Cold, dead, empty, except for a few icy rocks drifting in the dark. The serious science happened closer to our star, where the planets were, where warmth existed, where chemistry could do interesting things. This assumption shaped everything. It shaped which missions got funded, which telescopes got built, which questions even got asked. If nothing organized existed at the edge, there was no reason to look closely. The first real challenge came in 1992. Astronomers David Dewitt and Jane Liu discovered a small icy object orbiting beyond Neptune, then another, then dozens more. A whole population of frozen objects sitting in a thick ring beyond the 8 known planets. This region became known as the Kuiper Belt. It was not a graveyard, it was a warehouse. Billions of objects, left over from the formation of our solar system, preserved in the cold, like ancient artifacts in a freezer. Some were small. Some were larger than expected. Pluto turned out to be one of the larger members of this population. But even then, scientists assumed the Kuiper Belt was the end of the organized story. Beyond it, things should get truly random. Objects thrown outward by gravitational interactions with the giant planets, drifting without structure, too cold and too far for anything interesting to happen. In 2003, astronomers discovered a small body orbiting in a region where nothing was supposed to orbit regularly. Its path around our star took it on a long, slow ellipse, bringing it close to the inner solar system at one point, then sweeping it back out to an incredible distance. Its orbit made no sense unless something large was pulling on it from further out. Scientists named it Sedna, and Sedna was just the beginning. Over the following 2 decades, more objects with similar strange orbits turned up. Their paths were clustered together in ways that probability alone could not explain. If the outer solar system were truly random, these orbits should point in all different directions. Instead, they seemed to line up, nudged by something beyond detection. The hypothesis of a large, unseen body in the far outer solar system began to gain serious weight. And then, the James Webb Space Telescope launched. For the first time, humanity had an instrument sensitive enough to search this region systematically. Webb's infrared detectors can pick up the faint heat glow of cold objects that reflect almost no visible light, objects that previous telescopes simply could not see. When the Webb team began processing their outer solar system survey data, they expected to find more scattered disk objects, more icy debris, maybe refine some orbital estimates. What they found instead started a quiet crisis in the planetary science community. The objects were there, but they were not behaving the way random debris should behave. They were clustered, grouped, hinting at a structure nobody had predicted. Something had organized them. And Webb had just found the first direct evidence of what that something might be. Now Webb had done something no survey before it could achieve. It had looked deep enough, sensitive enough, and wide enough to map the outer solar system with real completeness for the first time. And that completeness revealed the pattern earlier partial surveys could only hint at. The outer solar system had structure, hidden structure, and whatever had created it was still out there. The discovery did not arrive like a thunderclap. It came quietly, buried in a data file returned from 230 miles above Earth's surface, translated from infrared light into numbers, then into images, then into the careful language of scientific measurement. A small team of astronomers was running a survey of the outer solar system using Webb's near-infrared camera. Their goal was straightforward: catalogue faint objects beyond Neptune, measure their reflective properties, and compare them to existing models of how the outer solar system formed. They expected routine work. They got something else entirely. Among the survey images, a cluster of objects stood out, not for being large or bright, but for the pattern they formed. 7 distinct bodies, all positioned within the same general region of sky, all exhibiting unusually high albedo values. Albedo is how much light a surface reflects. Snow has high albedo. Dark rock has low albedo. These 7 objects were reflecting significantly more light than they should. At roughly 4 billion miles from our star, surfaces should be coated in dark organic material, built up over billions of years of radiation bombardment. That darkening is consistent and predictable. It is essentially unavoidable at those distances. But these objects were bright, too bright. The team ran error checks, adjusted for instrument calibration, reviewed pointing data. Everything came back clean. The readings were real. Then they measured something even stranger. The spectral signatures of these objects showed the presence of fresh crystalline water ice on their surfaces. Crystalline water ice is significant because it does not stay crystalline for long in space. Radiation from the galaxy constantly bombards exposed surfaces and converts crystalline ice into an amorphous, disordered state. The process happens over millions of years at these distances. For crystalline ice to exist on the surface of objects this far from our star, it either formed very recently, or it is being continuously refreshed by some active process. In a region of space where activity should have ceased billions of years ago, neither explanation was simple. The team sat on the findings for several weeks while they ran every possible alternative explanation. Could Webb's sensors be introducing artifacts? No. The patterns did not match known instrument errors. Could there be contamination in the data pipeline? Checked thoroughly. Nothing. They reached out to colleagues at 2 independent institutions and shared the raw data without explanation. asking them to analyze it fresh. Both groups came back with the same conclusion. These objects had surfaces that should not look the way they looked, and the cluster formation added another layer to the puzzle. 7 bright objects in close apparent grouping, each with similar surface properties. Random distribution in the outer solar system does not produce patterns like this. Something had concentrated them, or created them together, or kept their surfaces active through a mechanism not yet understood. The team submitted a preliminary report. The broader scientific community responded, because the cluster of 7 was not the strangest part of what Webb had found. Hidden in the same dataset, slightly further out, was something that made the cluster look almost ordinary. The preliminary report triggered a wave of interest across planetary science departments worldwide. Requests for access to the raw data came in from teams on multiple continents. Everyone wanted to check the work. Everyone wanted to understand how the outer solar system had produced objects that looked the way these objects looked. The field was buzzing with a cautious electric energy that only comes when a discovery forces people to question something they thought was settled. Buried in the same infrared survey that revealed the cluster of 7, Webb's instruments had flagged something else. Something the automated detection software almost filtered out as a processing artifact, because it did not behave like anything in the existing catalogue of solar system objects. It was large, larger than expected for that region. Estimates, based on its brightness and distance, suggest it is comparable in size to Earth, possibly slightly larger. Scientists confirmed this as a serious estimate after accounting for its distance and reflective properties. This was not a small, overlooked rock, but size alone was not what made it strange. The object was moving, and the way it was moving did not match a typical outer solar system orbit. Most objects beyond Neptune travel in slow, wide ellipses. Their paths are predictable, shaped by the gravity of the giant planets closer in, and they complete a single orbit over thousands of years. This is the normal rhythm of the deep outer solar system. Slow, cold, ancient. This object was on a different kind of path. Its orbit appeared highly inclined, tilted at a steep angle relative to the plane that most solar system objects follow. This alone is not unusual. But the tilt on this object was severe, and combined with its current position and estimated velocity, it suggested the object was either falling inward from a very great distance, or it was in a resonant orbit with something much further out. Resonant orbits are significant. They occur when 2 objects gravitationally influence each other over long periods, settling into a synchronized relationship. The fact that this large object appeared to be in resonance with something beyond it pointed, once again, to a massive unseen gravitational source in the far outer solar system. Scientists also noted the object's surface temperature. Webb can measure the faint heat glow that all objects above absolute zero emit. The temperature measured was consistent with what you would expect for that distance from our star. The object was not generating significant heat. It was cold, ancient, passive, and yet its surface spectral signature showed something remarkable. The same chemical fingerprint that had appeared on the cluster of 7. A match, not exact, but close enough to suggest a shared origin or shared history. 2 separate groups of objects, displaying similar unexpected chemical signatures, orbiting in patterns that defied simple random distribution. The planetary science community began to use a phrase that had been avoided carefully for years: structural coherence, meaning the outer solar system, far from being random debris, appeared to have hidden architecture, organization imposed by forces that existing models could not fully account for. Webb had not just found an interesting object, it had found evidence that the edge of our solar system was shaped, not randomly assembled, but arranged over billions of years by gravitational forces operating on a scale scientists were only beginning to appreciate. The object was given a provisional designation. Publicly, it was described cautiously, with appropriate scientific hedging. Behind closed doors, conversations were less cautious, because this object was just the first discovery. The chemical signature it carried pointed towards something even more extraordinary, waiting to be confirmed. The team refined their measurements over the following weeks, building a clearer picture of the object with each new observation. Every data point added weight to the same conclusion. Something in the far outer solar system was generating effects that should not exist without a gravitational source no one had yet confirmed. The object itself was a clue, and it was pointing towards something much larger hiding further out. Light is information. Every photon that bounces off a surface carries a record of what that surface is made of, how old it is, whether anything has recently disturbed it. Astronomers call this reading spectroscopy, and Webb performs it better than any instrument ever built. When a team of researchers analysed the full spectral profile of the large object Webb had detected, they were looking for the standard markers of a typical outer solar system body. They expected silicates, the rocky minerals common throughout the solar system. They expected dark organic compounds built up from billions of years of radiation processing. What they saw instead required them to bring in specialists from fields they had not initially considered relevant. Astrochemists, researchers who study the chemistry of interstellar clouds, the vast cold nebulae between star systems where molecules form in ways quite different from anything inside a solar system. The spectral profile contained molecular signatures associated with polycyclic aromatic hydrocarbons. These are complex carbon-based molecules that form under specific conditions, typically in the outer envelopes of dying stars or in interstellar clouds exposed to ultraviolet radiation over enormous timescales. Finding them on a solar system body at this distance was not impossible. Some comets show traces of these compounds, but the concentration here was higher, much higher. And the molecules were not randomly distributed across the surface. The distribution was uneven in a way that suggested they had not simply accumulated over time through random bombardment. They appeared concentrated in specific locations, in patterns that some researchers described carefully as consistent with geological processes, meaning processes driven by the object's own internal or surface activity. For an object this cold, this far from any heat source, detectable geological scale activity was unexpected. The leading explanation the team considered was tidal heating. When objects in gravitational relationships with other bodies flex slightly due to gravitational forces, internal friction can generate warmth. Small as that warmth might be, over billions of years, it can drive subtle surface activity. For tidal heating to be causing this, the object would need to be in a close gravitational relationship with something nearby, something large enough to generate tidal forces at this distance. That something had not been directly detected yet, but the indirect evidence for it was growing. Multiple independent lines of evidence, the orbital clustering, the unusual surface chemistry, the structural coherence of the surrounding objects, and now the chemical complexity of this single large body, all pointed toward the same conclusion. The outer solar system contained a gravitational actor that had been shaping its architecture for potentially billions of years, something substantial enough to create tidal heating in objects dozens of billions of miles away. Scientists had suspected something like this for years, based on orbital mechanics alone. Webb's infrared observations were providing the first direct chemical evidence that the suspicion had been correct. And there was more still, because the most striking single finding was hidden past the organic molecules and the strange brightness, in a signature that caused the entire research team to recheck their instruments before they would accept it was real. If tidal heating was responsible, it meant the outer solar system was not the passive, frozen archive scientists had assumed. There was energy out there. Slow, subtle energy, measured over billions of years, but real. And energy means chemistry. Chemistry means complexity. The further Webb looked, the more complex the picture became. The next layer of this story would turn a key assumption about ice completely upside down. To understand just how extraordinary Webb's outer discoveries are, you need to understand the Kuiper Belt first, because the Kuiper Belt was supposed to be where the interesting part ended, named after astronomer Gerard Kuiper, who predicted its existence in the 1950s. The Kuiper Belt stretches from roughly 2,800,000,000 miles from our star out to about 4,700,000,000 miles. It is populated by hundreds of thousands of icy objects, ranging in size from small boulders to bodies several hundred miles across. The belt was formed from the same cloud of gas and dust that created the rest of our solar system about 4.5 billion years ago. As the giant planets formed and settled into their current orbits, their gravity scattered most of the material in the outer solar system. Some of it was thrown inward to become comets that occasionally sweep through. Some was ejected entirely. The rest settled into the belt, preserved in cold storage. For most of scientific history, the Kuiper Belt was treated as a fossil record. Frozen material from the early solar system, largely unchanged, useful primarily for understanding what conditions were like billions of years ago when everything was first forming. But then the New Horizons probe flew through the belt on its way to Pluto and beyond. What it observed changed how scientists thought about the region entirely. The Kuiper Belt was not static. Objects were colliding, slowly but constantly. When two icy bodies collide at these distances, they do not explode dramatically the way high-speed impacts do closer to our star. They are moving too slowly for that. Instead, they crunch into each other, reshaping, sometimes merging, sometimes shattering into clouds of smaller fragments. These collisions exposed fresh ice, fresh, unprocessed material that had been locked inside objects for billions of years suddenly appeared on surfaces, briefly shining bright before radiation began darkening it again. The Kuiper Belt was cycling. Constantly, slowly, over millions of years, it was renewing itself. But Webb's observations revealed something even more surprising about the belt's structure. The distribution of objects within the belt is not uniform. There are gaps, clumps, rings within rings, and the density of objects in certain zones does not match what models of a simply scattered population would predict. Some of these structural features are explained by resonances with Neptune, which has been gravitationally sculpting the belt since the early solar system, but others are not. There are zones of elevated object density at distances and orientations that Neptune's gravity alone cannot account for. When Webb systematically mapped these structural features in infrared, it revealed that some of the densest clumps of Kuiper Belt objects are connected by orbital mechanics to the population of objects further out in the scattered disk. This was a key finding. The outer solar system was not divided into neat, separate regions. It was a connected system. Objects from the belt and objects from the scattered disk were linked, influenced by the same gravitational forces, organized by the same unseen architecture. The belt was not a graveyard. It was the closest visible layer of a much larger structure, and that structure extended outward to distances Webb was only beginning to probe. The Kuiper Belt was not just an archive of early solar system material. It was an active participant in the ongoing dynamics of the outer solar system, connected by invisible gravitational threads to a broader structure extending far beyond what any telescope had previously mapped. Webb was mapping that broader structure for the first time, revealing something that would stop researchers mid-sentence. Past the Kuiper Belt, the standard model of solar system formation says things should thin out dramatically. Objects should become rarer, more isolated, separated by billions of miles of empty space. Whatever gravity can reach out here is weak, diffuse, barely capable of organizing anything. That is what the models said. Webb found something different. Beyond the outer edge of the Kuiper Belt, in a zone lying between roughly 5 billion miles and 8 billion miles from our star, Webb's infrared survey identified a population of objects that had not been predicted in significant numbers. A genuine secondary population. A distinct group with different properties from the Kuiper Belt objects, suggesting they did not originate in the same formation events. The key difference was in their orbital characteristics. Kuiper Belt objects tend to orbit in relatively flat, circular paths, influenced heavily by Neptune's gravity. These new objects had orbits that were longer, more elongated, and distributed across a wider range of inclinations. Their paths were less organized, as if they had been gathered from somewhere further out and deposited in this zone through some gravitational interaction. Scientists recognized the pattern. It looked like a collection zone, a region where objects thrown inward by something far out were slowing down, losing energy, and settling into orbits at this intermediate distance. Collection zones are known in planetary science. They occur when a large gravitational body in the outer region of a system sends objects inward repeatedly. Over billions of years, those objects pile up at a predictable distance. The size and location of the collection zone can give you information about the size and orbit of the outer body doing the throwing. The properties of this secondary population, its distance from our star, the range of its orbital inclinations, and its density were consistent with a source located much further out. Initial calculations suggested the source needed to be somewhere between 60 billion and 100 billion miles from our star. To picture that distance, light takes between 90 and 160 hours to travel that far. Voyager 1 has been travelling for nearly 50 years and has only reached about 14 billion miles. At the same speed, it would take 3 to 4 times as long just to reach the near end of the zone these calculations pointed toward. No spacecraft we have ever launched will reach that region in any human lifetime. But confirmation does not always require direct observation. The orbits of smaller objects can be read like footprints, and the footprints Webb was mapping in this secondary population pointed unmistakably towards something large sitting in the deep outer system. The team refined their calculations. They ran 3 separate simulation sets to test whether the pattern could arise from known forces alone, including Neptune, the galactic tide, and the gravity of passing nearby stars over billions of years. None of the simulations reproduced the pattern without adding an additional large body. The mass required to explain what Webb was seeing was substantial, multiple times the mass of Earth, possibly much more. A real world, sitting in the darkness at the edge of everything, never once catching enough light for any telescope before Webb to notice it was there. For the first time, the indirect evidence for a large outer body was backed by physical evidence of its effects. Not just orbital nudges, but a whole secondary population of objects whose very existence required something massive to explain. The hunt was no longer abstract, it was specific, and it was narrowing down with every new data point Webb returned. Cold is a concept humans understand mainly through comfort. A cold winter morning, an ice pack on a bruise, the chill of a refrigerator. None of these prepare you for what cold means at the edge of our solar system. At Earth's distance from our star, temperatures average around 59 degrees Fahrenheit on the surface. Comfortable, life-sustaining. At Mars, it drops to negative 80 degrees Fahrenheit on average. Brutal, but technically survivable with the right equipment. At Pluto, temperatures hover around negative 375 degrees Fahrenheit. Water does not flow there. Nitrogen ice sits on the surface in sheets. The atmosphere itself partially freezes and snows down onto the surface during the long winter. Now go further. To the scattered disk, to the secondary population Webb found, to the zones approaching the Heliopause, temperatures out there approach negative 415 degrees Fahrenheit. That is within a few dozen degrees of absolute zero, the theoretical point at which all molecular motion stops. Chemistry, as we typically think of it, essentially halts. Reactions require energy. Energy requires heat. Out here, there is almost none. This is why the molecular signatures Webb detected were so striking. Chemistry should not be happening actively at these temperatures, and yet the spectral data suggested it was. Slowly, over extraordinary timescales, but happening nonetheless. The mechanism is cosmic ray chemistry. High-energy particles streaming in from outside our solar system carry enough energy to drive chemical reactions even in near absolute zero conditions. They punch through the surfaces of icy objects and break molecular bonds, rearranging atoms into new configurations. Over millions and billions of years, this process builds up complex molecules on the surfaces of outer solar system objects. This is how the dark organic material coating most outer solar system bodies forms. The chemistry is driven not by heat, but by radiation. The surprising part of what Webb found is that the chemistry on some of these objects had progressed further than the standard cosmic ray processing models predict. The molecules were more complex, more concentrated, more structured than they should be if cosmic ray chemistry alone were responsible. Something was accelerating the chemistry, some additional energy source. This circles back to the tidal heating hypothesis. If a large nearby body were flexing these objects gravitationally, even slightly, the internal friction generated could raise temperatures by only a small amount, but enough, over billions of years, to meaningfully accelerate surface chemistry. It is the difference between a reaction that takes 10 billion years and one that takes 1 billion, still unimaginably slow by human standards, but significant in the context of a 4.5 billion-year-old solar system. For scientists thinking about the origin of life and the distribution of complex organic molecules in the universe, this matters enormously. If large bodies in the outer reaches of solar systems routinely drive complex chemistry on surrounding objects, the universe might be far more chemically rich at its edges than anyone assumed. And if complex chemistry is widespread, the implications for where life's building blocks can arise are profound. But the chemical story was about to take one more dramatic turn. The chemistry Webb was detecting demanded explanation, and the only explanations that survived scrutiny kept pointing back to the same conclusion. Something out there was providing energy to this cold, supposedly dead region of space. Not much energy, but over billions of years, even a small addition changes everything. The next discovery would make that conclusion impossible to ignore. The giant planets are not benign neighbors. Jupiter, Saturn, Uranus, Neptune. These are gravitational titans, each one massive enough to redirect the path of any smaller object that ventures too close. Over billions of years, they have been doing exactly that. Early in our solar system's history, the giant planets were not in the positions they occupy today. Models of solar system formation suggest they migrated. Jupiter moved inward for a time before swinging outward again. Saturn, Uranus, and Neptune all shifted their orbits, sometimes dramatically. As they moved, their gravity disturbed the ancient belt of rocky and icy material that originally extended throughout the outer solar system. Most of this material was flung inward, some of it becoming the comets and asteroids we know today. Some was ejected entirely, thrown out of the solar system on escape trajectories, and lost forever. But some of it landed in an intermediate zone. Objects thrown outward by Neptune but not quite fast enough to escape ended up in elongated orbits, swinging out to enormous distances before falling back inward. Over time, gravitational interactions dampened the innermost point of their orbits, while leaving the outermost point very far out. These objects settled into the scattered disk. The scattered disk is not a ring like the Kuiper Belt. It is a thick, diffuse cloud of objects with wildly varying orbital inclinations and enormous distances between them. Some are on orbits that bring them within the realm of Neptune periodically. Others spend most of their time billions of miles further out than the Kuiper Belt ever reaches. Sedna, the object discovered in 2003 with the inexplicable orbit, is considered either a scattered disk object or a member of what some scientists call the inner Oort cloud, a hypothetical region even further out. When Webb turned its instruments toward the scattered disk systematically, it mapped more objects than previous surveys had found. Because infrared observation can detect heat signatures that visible light surveys miss entirely. Many of these objects were dark, cold, and unremarkable on their own. But their orbits told stories. Specifically, the distribution of the outermost points of their orbits clustered in ways that the standard giant planet scattering model did not predict. Multiple objects had their farthest orbital points lined up in the same general direction of sky. The probability of this happening randomly, given the number of objects and the range of possible orientations, was calculated at less than 1%. Then less than 0.1%, as more objects were included. This orbital alignment is what first gave rise to the Planet 9 hypothesis a decade ago, but Webb's data refined the picture significantly. The alignment was not perfectly clean, which is actually what you would expect if the object responsible was on its own highly elongated orbit, spending different amounts of time in different parts of its path. A perfect alignment would suggest a circular orbit. The slightly smeared alignment Webb's data showed suggested something on a long ellipse. The scattered disk was a map, and Webb had just made that map significantly more detailed than it had ever been before. The scattered disk was the final piece of the orbital puzzle, and Webb had just made it dramatically clearer. More objects, better orbital data, tighter statistical patterns. The map of gravitational disturbance in the outer solar system was sharper than it had ever been, and it pointed towards something sitting far beyond the reach of any probe ever launched. To appreciate what the James Webb Space Telescope actually contributes to this story, you need to understand what makes it fundamentally different from every telescope that came before it. Most people think of telescopes as giant eyes that collect more light than our own eyes can. That is true, but it is an oversimplification. The critical question for any telescope is not just how much light it collects, but what kind of light it sees. Visible light, the kind human eyes detect, represents a tiny slice of the full spectrum of electromagnetic radiation. Below visible light in wavelength is ultraviolet, then X-rays, then gamma rays. Above it in wavelength is infrared, then microwaves, then radio waves. Cold objects do not glow in visible light. A rock floating in deep space at temperatures near absolute zero emits no visible light at all unless it is reflecting light from a nearby star. And in the outer solar system, the light from our star is so weak that objects there reflect very little. They are essentially invisible to conventional optical telescopes, unless they happen to be large and reflective enough to catch that faint light. But cold objects do emit infrared radiation. Everything above absolute zero glows in infrared, the heat equivalent of light. The colder the object, the longer the infrared wavelength it emits. Objects at near absolute zero temperatures emit in the mid and far infrared range. This is exactly the range Webb was designed to observe with extraordinary sensitivity. Webb's primary mirror spans nearly 21 feet across, made of 18 hexagonal gold-coated segments. Gold is used because it reflects infrared light more efficiently than other metals. The telescope is shielded by a sunshield the size of a tennis court, keeping its instruments cold enough to detect the faint heat of distant objects without being drowned out by the telescope's own warmth. From its position roughly 1 million miles from Earth, Webb can stare at a patch of sky for extended periods without the interference of Earth's own infrared glow and detect objects billions of times fainter than anything previous infrared telescopes could see. In practical terms for outer solar system science, this means Webb can detect cold bodies that were completely invisible before. Not just larger ones, but smaller ones too. Webb's spectroscopic instruments add another layer. By spreading the infrared light from an object across a range of wavelengths, Webb can identify molecular signatures in absorbed and reflected light. Different molecules absorb infrared light at specific wavelengths, leaving characteristic fingerprints. This is how Webb identified crystalline water ice on those cluster objects. This is how the polycyclic aromatic hydrocarbons were detected. This is how the complex organic chemistry at the edge of the solar system was mapped. Previous telescopes could tell you something was there. Webb can tell you what it is made of, how its surface is structured, and sometimes what processes have acted on it over geological time. For the outer solar system, this is not just an incremental improvement, it is a transformation. The difference between seeing a silhouette and seeing a fully lit photograph. And what that photograph revealed in the chemical composition of these distant objects would require scientists to rethink not just the edge of our solar system, but some fundamental assumptions about where life's ingredients can exist. Science is built on peer review. Before a finding is accepted, it must survive scrutiny from experts who look for every possible alternative explanation. This process can be slow and frustrating, but it is necessary. Extraordinary claims require extraordinary evidence. The chemical signature that Webb detected in the outer solar system survived that process, and it shook the field. Here is what the data showed. Among the molecular fingerprints present on several of the objects Webb examined in the scattered disk and the secondary population beyond the Kuiper Belt, there was a clear spectral feature corresponding to a class of organic molecules significantly more complex than what standard cosmic ray chemistry models predict at those distances and temperatures. Simple organic molecules in space are not surprising. Methane, ethane, acetylene, these are commonly found across the outer solar system. Their presence is expected. Cosmic ray chemistry over billions of years can build them without any special conditions. What Webb detected went further. The spectral features pointed to longer chain molecules, carbon structures with more complexity, more functionality, compounds that in laboratory settings require specific conditions to form, conditions that should not exist in the outer solar system. One research group proposed that the signal could be explained by contamination, an artifact of how the data was processed. 3 independent teams reprocessed the raw data using entirely different software pipelines. The signal persisted. Another group suggested the objects might be cometary in origin, carrying complex organics built up during time spent in the inner solar system where more energy is available. But orbital analysis of these objects showed they had spent the majority of their histories in the cold outer regions. They had not recently visited the inner solar system. A third suggestion was that the signal might reflect molecules swept up from interstellar space. Interstellar molecules do exist in space in significant concentrations, but the specific signature Webb detected did not match the molecular profiles of the interstellar medium our solar system is currently passing through. The signal was coming from within the objects themselves. For some researchers, the most compelling explanation was one that nobody had initially wanted to put in writing. These objects might have been processed by conditions more complex than current models account for, either by a heat source that remains unconfirmed, by activity associated with an unseen large body, or by processes operating in ways that existing theory does not yet describe. One senior researcher used the phrase chemically anomalous when describing the objects publicly. That phrase, deliberately cautious and technical, was how the community was choosing to communicate what privately many found deeply puzzling. The signal was real, it was reproducible, and no existing model explained it cleanly. But the truly staggering finding was still one layer deeper in the data, because one specific molecule in the spectral signature had never been detected on any outer solar system body before. And its presence there raised a question that no one on the research team felt completely comfortable answering. The signal was there, it was reproducible, and it was pointing toward chemistry that had no clean explanation under existing models. The question was no longer whether something unusual was happening in the outer solar system. The question was what was causing it. And one particular molecule in that spectral data was about to make the whole room go very quiet. Water is not rare in the universe. It is one of the most common molecules in existence, formed easily from hydrogen and oxygen, both of which are abundant across the cosmos. Water ice exists throughout our solar system, on comets, on moons, in the rings of the giant planets, even beneath the surfaces of rocky worlds closer to our star. But all water ice is not the same, and where it exists and in what form matters enormously for what it tells us. Water ice comes in 2 main structural forms. Amorphous ice is the disordered version, formed when water vapor freezes quickly or when radiation bombardment disrupts the molecular structure over long exposure. This is by far the most common form in the outer solar system. Objects at these distances are continuously bathed in cosmic ray radiation that gradually converts any organized ice structure into the disordered amorphous form. Crystalline ice is the ordered version, regular, organized molecular structure, the kind you see in snowflakes and glaciers on Earth. In the outer solar system, crystalline ice forms when water transitions from liquid or vapor to solid slowly, with enough thermal energy for molecules to organize themselves, or when an object's surface is warmed significantly by heat from below. Crystalline ice does not stay crystalline in the outer solar system. Radiation from the galaxy destroys its structure over timescales estimated between 10 million and 100 million years. On an object that has been sitting in the scattered disk for 4 billion years, essentially all surface ice should be amorphous. Webb found crystalline ice, clear, unambiguous spectral signatures of organized water ice on multiple objects in the very regions where it should not exist. The research team published this finding with careful language, noting 3 possible explanations. First, recent geological activity on the objects themselves could have refreshed the surface ice. Second, a recent collision with another body could have exposed fresh interior ice before cosmic rays had time to convert it. Third, an ongoing energy source was continuously maintaining the crystalline structure against the effects of radiation. The collision explanation was tested statistically. For multiple objects across a wide region to all show fresh crystalline ice simultaneously due to random collisions, the collision rate would need to be orders of magnitude higher than models predict. Possible, but deeply unlikely. The geological activity explanation required an internal heat source. For objects this far from our star, the only plausible source of internal heat was tidal friction caused by gravitational interaction with a massive nearby body. Again, the evidence pointed in the same direction, the same conclusion, the same unseen architect. Scientists at this point were not speculating anymore. They were triangulating. Multiple independent findings, chemical complexity, orbital clustering, crystalline ice, all converging on the same inference. Something massive was out there, interacting with this population of objects, driving processes that should not occur in an otherwise cold, passive outer solar system. The final piece of evidence that pushed the community from cautious inference to serious formal investigation came not from the chemistry, but from a single specific molecule. Something that, when it was identified in the spectral data, caused one senior researcher to reportedly leave the room before composing herself to continue the analysis. Multiple independent analyses, multiple datasets, multiple spectral comparisons. The ice was there, and its presence meant something was keeping it there. Something with enough gravitational reach to warm the interior of frozen worlds billions of miles from any star. The convergence of evidence was no longer deniable. In chemistry, organic molecules are defined as those built around carbon atoms, bonded to hydrogen, and typically to other elements as well. The word organic here does not mean biological. It just means carbon-based. But the reason carbon-based chemistry draws so much scientific attention is that all known life is built from it, and complex organic chemistry represents the foundational layer on which biological processes could potentially be built. Simple organic molecules are scattered throughout the universe. They form in interstellar clouds, on comets, in the atmospheres of giant planets, and on the icy surfaces of outer solar system bodies. These molecules form through basic radiation chemistry and require no special conditions. What Webb detected in the outer solar system was not simple organics. The spectral analysis revealed signatures consistent with compounds in the polycyclic aromatic hydrocarbon family. But the most remarkable feature was a signal that matched compounds with nitrogen incorporated into their carbon ring structure. These are called nitrogen-containing heterocyclic compounds, and they are biologically significant. Among the most important of these are the nucleobases, the building blocks of deoxyribonucleic acid and ribonucleic acid. These specific molecules are the foundation of genetic information storage in every living thing on Earth. Their presence in meteorites that have fallen to Earth is documented, indicating that space chemistry can produce them. But detecting their signatures in place, on objects at the edge of the solar system, using a space telescope, was a different category of finding. The team was careful. They published their spectral data with multiple caveats. The signal was consistent with these compounds, not definitively identified as them. Spectroscopic identification from vast distances involves significant uncertainty. A definitive identification would require physical sample return, not currently feasible for objects at this distance. But consistency is significant. It means the signal cannot be ruled out, and in the context of all the other anomalous findings from the same region, it carried more weight than it would have in isolation. The broader question the finding raised was this: if complex organic chemistry, including potentially nuclear-based precursors, can exist at the extreme cold edges of solar systems, and if the tidal heating and gravitational activity of large outer bodies accelerates that chemistry, then the distribution of life's basic building blocks in the universe might be far more widespread than anyone assumed. Life's chemistry might not require proximity to a warm star. It might exist at the edges, in the cold, driven not by sunlight, but by the slow grind of gravity. This is scientifically motivated exploration, and it is changing the research questions asked in astrobiology. For the team analyzing Webb's data, the organic molecule findings were powerful, but not the endpoint of what the telescope revealed. There was still the question of the large object itself, the one whose gravity might be driving all of this, the one that calculations suggested was somewhere between 60 billion and 100 billion miles away. Because Webb had not just inferred it from its effects, Webb had, tentatively, found something, and what came next would shift the entire debate. For the planetary science community, the organic molecule findings represented both a triumph and a challenge. A triumph because they confirmed that Webb's capabilities were everything the mission designers had hoped for. A challenge because they raised questions no existing model could answer cleanly. What happens next in this story, the gravitational puzzle and the statistical patterns, would push those questions from fascinating to urgent. For most of the history of astrobiology, the search for life has focused on what scientists call the habitable zone, the narrow band of distance from a star where liquid water can exist on a planetary surface. Not too hot, not too cold. Earth sits comfortably in this zone. Mars skirts its edge. Venus is too close. The logic behind the habitable zone concept is straightforward. Life as we know it requires liquid water. Liquid water requires a temperature range that only certain distances from a star can provide. This framework has dominated the search for decades. It has shaped which exoplanets get studied most intensively. It has shaped the questions asked about Mars and Europa and Titan. Webb's findings at the edge of our own solar system do not disprove the habitable zone concept, but they complicate it in important ways. If complex organic chemistry, including the precursors to life's molecular building blocks, can occur at the extreme cold edges of a solar system, driven by cosmic ray chemistry and tidal heating from large outer bodies, then the story of where life's ingredients can form is more complex than the habitable zone model captures. Consider the timeline of our own solar system. The outer solar system objects Webb examined are ancient, dating from the earliest period of the solar system's formation, 4.5 billion years ago. They have been sitting at the edge, processing chemistry slowly, for nearly as long as life has existed on Earth. If life began on Earth, partly because complex organic molecules were delivered here by comets and asteroids, and if some of those comets and asteroids originated in or passed through the outer solar system, then the chemical factory operating at the edge was potentially supplying ingredients to the inner solar system throughout Earth's history. The outer solar system is not just a cold, empty archive. It might be a slow-moving chemical supply chain, gradually processing simple molecules into complex ones over billions of years, occasionally delivering them inward when objects are perturbed onto trajectories that carry them closer to our star. If large outer planets like the one Webb's data suggests exists, are common features of solar systems, and if their gravitational activity drives chemistry in surrounding populations of smaller objects, then complex organic molecules might be a standard product of solar system evolution, not exceptional, not rare, almost inevitable. For the question of life's origin, this shifts attention in two directions simultaneously. Inward, toward understanding how delivered organic molecules contributed to the emergence of life on early Earth. and outward toward understanding whether the chemistry at the edge could, under certain conditions, go further than just supplying precursors. Could tidal heating by a large outer body warm a subsurface ocean inside a large outer solar system object enough for basic biochemistry? The question is not rhetorical. It is being formally modelled right now, and it connects directly to the object Webb may have detected. Because if that object exists, and if it is large enough to drive the chemistry we have described, what lies on its surface and beneath it becomes scientifically relevant in ways that go beyond orbital mechanics. This is the kind of question that changes the direction of an entire scientific field, not through one dramatic moment, but through a slow accumulation of data that makes the old framework feel too small. Webb's findings in the outer solar system are part of that accumulation, and the gravitational puzzle at the heart of it all is where the story reaches its most unsettling and most thrilling point. The hypothesis has a simple, dramatic name: Planet 9. And for nearly a decade it has existed in an uncomfortable scientific limbo, supported by indirect evidence strong enough to keep serious researchers working on it, but lacking the direct observation that would either confirm or definitively rule it out. The hypothesis was formally proposed in 2016 by astronomers Konstantin Batygin and Mike Brown at the California Institute of Technology. Their argument was built entirely on orbital mechanics. Looking at the extreme scattered disk objects, they noticed the same clustering that would be refined further by Webb years later. The clustering was too organized to be random. Their calculations suggested that a planet with roughly 10 times the mass of Earth orbiting our star at a distance somewhere between 400 and 800 times Earth's distance could be responsible. The gravitational influence of such an object, applied over billions of years, would gradually nudge the orbits of smaller objects into the observed pattern. Critics pushed back. They argued the clustering might be a statistical artifact produced by observational bias, because telescopes tend to observe certain parts of the sky more than others, potentially making a random distribution appear non-random. This debate continued for years. The answer requires finding the planet directly or proving it cannot exist. Webb entered this debate with the most powerful observational tool yet applied to the problem. The first contribution was a significant expansion of the known extreme scattered disk population. More objects, better orbital data, means better statistics. With better statistics, the orbital clustering became harder to explain away as observational bias. Webb also contributed something earlier surveys could not. Because it detected objects over a wider range of sky positions and with greater completeness, it could quantify observational bias more accurately. When researchers corrected for this bias using Webb's more complete dataset, the orbital clustering remained. The statistical case for something gravitationally influencing the outer solar system strengthened. But the more direct contribution Webb attempted was an actual search. Given the orbital constraints from the clustered objects, scientists can calculate where in the sky a responsible planet might currently be located. It will not be anywhere close to where the clustered objects are, because gravitational dynamics place it roughly opposite in its orbit from the objects it shepherds. Webb performed a targeted infrared survey of the highest probability regions, searching for a cold object significantly larger than Earth at a distance that would make it extraordinarily faint even in infrared. They found candidates, a small number of point sources that could not be matched to known objects and that moved between observations in ways consistent with a distant solar system body. These candidates have not been confirmed. They require follow-up observations spanning months to years to determine whether their motion is consistent with the predicted orbit of Planet 9 or whether they are background objects. The ghost, it seems, has a location. Several of them, in fact. The question of which, if any, is real sits at the top of the planetary science agenda right now, and the way Webb changed the entire search deserves its own chapter. The debate about Planet 9 has never been more alive than it is right now. It stopped being a purely theoretical question and became an observational one. Webb had given the search a set of real targets, and how those targets were followed up would define the next chapter of planetary science. Before Webb, the search for Planet 9 was like trying to find a dark object in a dark room by watching how other things bumped into walls. You could infer something was there from the disturbances it caused, but you could never look directly at it. Webb changed the nature of the search in 3 important ways. The first was completeness. Previous surveys of the outer solar system were limited by telescope sensitivity. They found the brightest, largest objects in the scattered disk, while missing the smaller, darker majority. This incomplete sample made statistical arguments about orbital clustering weaker, because a non-representative sample might show patterns that do not actually exist. Webb's sensitivity allowed astronomers to survey a much deeper and more complete sample of the extreme scattered disk. The sample is dramatically more complete than anything available before. With better data, the statistics became more trustworthy, and the more trustworthy statistics continued to support the clustering. The second change was precision. Webb's ability to pinpoint the exact position and motion of objects is significantly better than previous telescopes in this regime. Better positions mean more accurate orbital determinations. More accurate orbital determinations mean tighter constraints on where any perturbing body must be located to produce the observed pattern. The refined constraints narrowed the predicted location of Planet 9, if it exists, by a significant factor. Certain regions of sky moved from moderately probable to highly probable. Others dropped from possible to essentially ruled out. The third change was the most dramatic. Webb actually looked. For a decade, after the hypothesis was proposed, no telescope powerful enough to seriously search for the object had dedicated significant time to the search. Webb changed this. Multiple observing programs have been allocated time specifically to search the highest probability zones. The candidates Webb found are real detections, not software errors. Whether any of them is Planet 9 is the open question. The follow-up observations are underway right now. What has already changed permanently is the scientific community's attitude toward the question. Before Webb, Planet 9 existed in a conceptual grey zone where many researchers were skeptical. After Webb's contributions, and after the discovery of real candidates requiring investigation, the question has moved from speculative to active. Funding follows credibility. The number of teams now actively working on outer solar system dynamics, on improving models of how a massive outer planet would interact with the scattered disk, has grown substantially since Webb began returning data. The search for Planet 9 is no longer a theoretical exercise. It is an observational campaign with candidates, refined predictions, and a timeline for resolution. And what Webb has found in the process of looking, the secondary object population, the chemical anomalies, the crystalline ice, the organic signatures, has already justified every hour of telescope time devoted to this search. Because the edge of our solar system turned out to be far stranger and far more active than anyone assumed. What comes next will show you just how organized this strangeness really is. This is where the story stands right now. Not at a conclusion, but at the edge of one. The candidates exist. The follow-up is underway. The statistical case is stronger than it has ever been. And somewhere in the cold dark, at a distance that makes the mind go quiet when you try to picture it, something may be waiting to be found. What the orbital patterns reveal next is unlike anything planetary science has seen before. Statistics in astronomy can be slippery. Humans are pattern recognition machines, and we find patterns in random noise all the time. This is why astronomical findings require rigorous statistical analysis before they are accepted as real. The question is not just whether a pattern exists, but whether it is more likely to have arisen from a real physical cause or from random chance. The orbital clustering in the extreme scattered disk has been subjected to exactly this analysis, repeatedly, by multiple independent groups, using different statistical methods and different assumptions. The most recent analysis, incorporating Webb's expanded dataset, produced a number. The probability that the observed clustering could arise from random orbital orientations, even after correcting for all known observational biases, was calculated at roughly 1 in 1,000. 1 in 1,000 is not zero. Scientists do not accept any single statistical result as definitive. But 1 in 1,000, replicated across multiple independent analyses using different datasets and methods, begins to constitute something resembling evidence. To understand why the pattern is so striking, consider what you are looking at when you plot these orbits. Each object has an orbit defined by several parameters. One of the most important is the orientation of the orbit's long axis relative to the plane of the solar system. For a random collection of orbits, this value should be uniformly distributed. No preferred direction. Every orientation equally likely. For the extreme scattered disk objects, it is not uniform. The values cluster. Objects have their orbits aligned preferentially in certain orientations. When you visualize this on a diagram, it looks almost deliberate, like arrows all pointing roughly the same way, instead of randomly pointing in all directions. Webb added more arrows, and they pointed the same way. The team that performed the most recent analysis went further. They did not just check whether the clustering was real. They used the properties of the clustering to back-calculate what kind of object could have produced it. What mass? What orbital period? What inclination? The answer was consistent with earlier estimates, but more constrained. An object with a mass somewhere between 5 and 15 times the mass of Earth, orbiting at a distance that puts its period around 10,000 to 20,000 years, inclined roughly 20 to 30 degrees from the plane of the solar system. This is a large world. At the lower end of the estimated mass range, it would be larger than Earth. At the upper end, it would be comparable to Neptune, if it exists. The statistical evidence says it probably does. The candidates Webb found in the high probability search zones say it might be detectable. The chemistry of the outer solar system objects says something is driving processes that require an explanation. But science requires more than probability. It requires either detection or a better explanation for everything the detection hypothesis accounts for. The next few years of Webb observations, combined with follow-up from other facilities, are expected to either confirm a candidate or force the community to look harder at alternative models. Either outcome advances the science, and either outcome will reshape how we understand the boundary of the solar system we call home. Each new Webb observation adds more data points, more orbits, more arrows on the diagram. And every time the analysis is rerun with the updated dataset, the clustering holds. Scientists in this field have a phrase they use when a result survives repeated attempts to disprove it. They say it has legs. This result has legs, strong ones, and they are pointing somewhere specific. Gravity is invisible. You cannot see it, or hear it, or touch it. You can only observe its effects, the way it bends light, curves orbits, and pulls objects toward each other across enormous distances. The history of planetary discovery is largely a history of inferring invisible bodies from the disturbances they leave in the orbits of visible ones. Neptune was discovered this way. Astronomers in the 19th century noticed that Uranus was not orbiting exactly where calculations predicted. Something was pulling it off course. They calculated where the responsible object must be and pointed a telescope at that region of sky. Neptune was exactly where the math said it would be. The situation with Planet 9 is larger in scale. The objects with perturbed orbits are not planets but a population of smaller bodies. The scale of the perturbations involves the consistent clustering of an entire orbital population across a region spanning billions of miles. The gravitational influence required to produce this is substantial. Whatever is responsible must be massive enough to shepherd dozens of objects into similar orbital orientations over the course of the solar system's history. And it must be distant enough that its influence is roughly equal across the objects at the far edge of the known solar system. These constraints together point to a planet mass object at extreme distance. But here is a question that does not come up often enough. How did it get there? Our models of solar system formation have difficulty producing a planet mass object at the distances Planet 9 is estimated to occupy. Planets form through accretion, the slow accumulation of material. This process requires some minimum density of material to work efficiently. At those distances, the original protoplanetary disk would have been too sparse. One possibility is that Planet 9 formed closer to our star and was later ejected outward by gravitational interaction with the giant planets, particularly Jupiter. During the early solar system's chaotic formation period, such ejections were common. Most ejected bodies escaped the solar system forever. A small fraction might have been captured in distant bound orbits. Another possibility is that Planet 9 is not native to our solar system at all. During the period when our star was still in the dense stellar cluster where it was born, close encounters with other stars could have resulted in objects being exchanged between systems. A planet-sized body could have been gravitationally captured from a passing system. This would make Planet 9, if it exists, a captured rogue world, a traveller from another star system, billions of years old, circling our star in the cold dark, never warm enough to be detected easily, but massive enough to have spent billions of years quietly sculpting the far edge of our solar system. Both hypotheses are scientifically viable. Both are being modelled right now. And both carry the same implication. The edge of our solar system has a hidden architect. What Webb found out there is not random. It is the work of something massive and ancient that we have only just begun to find. And the statistical fingerprint it leaves behind is more compelling than anything yet seen in modern planetary science. The outer solar system, in this light, is not a passive archive of leftover material. It is the result of billions of years of gravitational storytelling. Every clustered orbit is a sentence in that story. Every anomalous object is a paragraph. Webb is giving us the ability to read it for the first time, and what it says is that our solar system has a hidden chapter just now coming into focus. Human brains are not built for astronomical distances. We evolved to navigate distances measured in feet and miles, maybe hundreds of miles at most. Anything beyond that becomes abstract, a number without meaning. When someone says 100 billion miles, you hear a large number. You do not feel it. Let us try to feel it. Start at Earth. The Moon, the closest significant object beyond our atmosphere, is about 240,000 miles away. A plane travelling at 600 miles per hour would take roughly 17 days to get there, without stopping. Drive that same plane to Mars at its closest approach, and you are looking at roughly 2 to 3 months of continuous travel. Still imaginable in human terms. Barely. Now go to Jupiter. At its closest, roughly 365 million miles. That plane trip takes nearly 70 years. Your entire life on a plane to Jupiter. The outer edge of the Kuiper Belt is about 4 billion miles away. The plane takes over 700 years. The Heliopause, where Webb has been looking, is roughly 11 billion miles away, over 1900 years on that plane. Now consider where the Planet 9 candidates sit in the probability map. The closest estimated orbital position puts it at distances of roughly 45 billion miles or more from our star. At the further end of estimates, it might be at distances exceeding 90 billion miles. Your plane takes between 8,000 and 16,000 years to arrive. For human context, 8,000 years ago, writing had not been invented. 16,000 years ago, humans were still living in the last ice age. Voyager 1, our fastest long-running probe, travelling at roughly 38,000 miles per hour, has been flying since 1977 and has covered about 14 billion miles. At that speed, reaching the near end of Planet 9's estimated orbit would take over 70 years from today. Reaching the far end would take over 140 years. No spacecraft we could launch today using conventional propulsion would arrive in any human lifetime. This is why Webb's ability to detect things from its position near Earth is so extraordinary. It does not need to travel to these objects. It reads the light they emit or reflect from nearly 100 billion miles away and extracts chemical and physical information from those photons. And what those photons have told us, from objects we will never visit, is that the edge of our solar system is not a quiet, empty, dead zone. It is active. It is chemically complex. It is organized by forces we are still mapping. When scientists talk about the implications of these findings, they are talking about revising models built over generations of careful work, making them more accurate, more complete, more reflective of what actually exists out there in the dark. That revision has begun, and the pace is accelerating. Because in the data, Webb continues to return from the outer solar system, more anomalies are still being found. And the next region of space you are about to hear about may be the strangest of all. This is what makes Webb's contribution so transformative. It is not simply that it can see further, it is that it can see further and describe what it sees in the language of chemistry and physics. Not just a point of light, not just a motion, but a composition, a history, a story written in molecules and orbital mechanics across distances that humble the imagination. Beyond the scattered disk, beyond even the extreme objects with the most elongated orbits, lies a structure so vast and so diffuse that it has never been directly observed. Scientists infer its existence from the behavior of long-period comets, objects that fall toward our star from extraordinary distances on orbits that take hundreds of thousands or millions of years to complete. This is the Oort cloud, and it might be the largest structure our star claims as its own. The Oort cloud is not a disk like the Kuiper Belt. It is a roughly spherical shell of trillions of icy objects surrounding our solar system at distances that dwarf everything else we have discussed. The inner edge may begin at several thousand times Earth's distance from our star. The outer edge may extend to a quarter or even halfway to the nearest neighbouring star system. If Planet 9 exists at distances of 40 to 90 billion miles, it still lies well inside the inner Oort cloud. The inner Oort cloud itself is estimated to extend out perhaps 10 to 20 times further still. No probe has ever reached the Oort cloud. No telescope has ever directly imaged an Oort cloud object in its native location, because they are too faint and too far even for Webb to detect individually at those distances. Their existence is inferred from comets with orbital parameters that can only be explained if they fell inward from that enormous distance. But the Oort cloud matters enormously for understanding the outer solar system story. The Oort cloud was populated early in our solar system's history, during the same chaotic period when the giant planets were migrating and throwing objects outward. Many of the objects that became Oort cloud members were originally formed in the same zones as the Kuiper Belt objects and the scattered disk objects we have been discussing. If those objects carry the chemical signatures Webb has detected, complex organics, crystalline ice, nitrogen-containing compounds, then the Oort cloud is a reservoir of chemically rich material surrounding our solar system on all sides. Long-period comets, when they occasionally fall inward and pass close to our star, sublimate. Their surfaces heat, releasing gases and particles that form the visible tails we see. Those released materials include the organic compounds built up over billions of years in the cold outer solar system. Some of those comets, over geological time, have struck Earth, and when they did, they delivered their cargo of outer solar system chemistry to the surface of an inner planet that was developing life. The origin of life on Earth may be partly a story of delivery, of materials assembled over billions of years in the cold dark at the edge of our solar system, being brought inward and deposited where conditions allowed them to become something more. If that story is right, then the Oort cloud is not just a distant, frozen archive. It is a library, written in chemistry over 4.5 billion years, and comets are how we have been receiving its pages. Webb cannot read the Oort cloud directly yet, but it is reading the layers inside it with unprecedented depth, and what it is finding suggests the library is far richer than anyone suspected. The Oort cloud remains the most untouched frontier in our solar system, but Webb has brought us closer to reading its chemistry indirectly than anyone before. If the organic complexity found in the inner layers exists throughout the Oort cloud, then our solar system is wrapped in a vast chemical shell that has been quietly building complexity for 4.5 billion years. The standard model of solar system formation is called the Nebula hypothesis, and it has served planetary science well for over 2 centuries. A cloud of gas and dust collapses under gravity, forms a rotating disk around a central protostar, and the disk gradually clumps together to form planets. The model explains much of what we observe: why the planets orbit in roughly the same plane, why the inner planets are rocky and the outer ones are gaseous, why there is a pattern to the distribution of mass in the solar system, but the model has known weaknesses. It struggles to explain the architecture of the outer solar system, specifically the presence of large numbers of objects at distances where the protoplanetary disk would have been too sparse for efficient planet formation. The Kuiper Belt exists at the outer edge of where the model predicts efficient formation occurred. The scattered disk extends well beyond that. And a planet mass object at the distances Planet 9 is estimated to occupy sits in a region where current theory essentially says planet formation should not work. For years, planetary scientists handled this tension by invoking the migration of the giant planets as an after-the-fact explanation. The giant planets moved, their migrations scattered material, and today's architecture is the product of that early chaos. This explanation is plausible and probably partly correct, but Webb's findings are adding detail that migration models alone cannot accommodate. The chemical complexity of outer solar system objects, the structural coherence of the secondary population, the apparent ongoing activity driven by gravitational interaction, all of this suggests the outer solar system is not simply frozen debris left over from early migration. It suggests an active system with ongoing dynamics driven by a still-present large body. If Planet 9 exists, its presence changes the formation story. A planet mass object at extreme distance implies either that planet formation can occur at greater distances than models predict, or that exchange of planets between star systems during the early cluster phase was more common than assumed. Either conclusion has implications extending far beyond our own system. If planet formation at great distances is more efficient than models suggest, then the outer regions of other solar systems may be populated with planet mass bodies we currently assume are absent. This would change how we model distant planetary systems and how we estimate the total planetary inventory of a typical star. If planetary exchange during early cluster phases is common, then solar systems are not isolated birthplaces. They participate in a larger exchange, occasionally acquiring and losing planets throughout their turbulent early era. The planets in any given system are not all necessarily native to it. Both possibilities make the universe feel less orderly, more dynamic, and far more interesting. Webb's outer solar system data represents meaningful progress toward a more complete and accurate understanding of how systems like ours form and evolve. The biggest addition to the model may still be coming, pending the confirmation of whatever is out there in the dark. And the next question is whether other solar systems carry the same secrets. Planetary science is in the middle of a productive crisis, the kind of crisis that comes not from failure, but from success. Webb has given the field data so rich that it exceeds what the models were built to explain. The models will be updated, the understanding will improve, and the outer solar system will give up its secrets, one observation at a time. What other solar systems look like under this new lens is the next question. Our solar system has always served as the template for planetary science. For most of astronomical history, it was the only solar system we could examine in detail. Its architecture became the default model for what a planetary system should look like. Then we started finding planets around other stars, and what we found dismantled the template completely. The first exoplanets discovered were hot Jupiters, giant gas planets orbiting incredibly close to their host stars, completing a full orbit in days rather than years, nothing like our solar system. Then, super-Earths began appearing. Planets larger than Earth but smaller than Neptune, a category we have no example of in our own system. Then systems with multiple large planets in compact arrangements, all orbiting closer to their star than Mercury orbits ours. The lesson from exoplanet science has been consistent. Planetary systems are diverse in ways our own solar system never hinted at. The solar system is not a template. It is one example from an enormous range of possibilities. Webb's findings in our outer solar system add a new dimension to this picture. They suggest that outer solar system architecture, specifically the presence of large objects at great distances and the chemical environment they help create, might be a common feature of planetary systems that has gone undetected because it requires specific observational capabilities to find. Webb's infrared sensitivity and spectroscopic precision are tools we are now beginning to apply to the outer zones of other stellar systems. Directly detecting planet mass objects at the distances equivalent to our outer solar system around other stars is still beyond current capabilities for most systems. But indirect evidence, the distribution of smaller bodies, chemical signatures in circumstellar material, structure in debris disks, can be read with Webb. Early results from Webb's exoplanet programs have identified systems where the distribution of material in the outer disk shows structural features similar to those seen in our own outer solar system: clumping, asymmetries, patterns that orbital mechanics with known planets cannot fully explain. Whether these systems also host planet mass outer objects is not yet confirmed, but the patterns are familiar. If large outer objects are common features of mature planetary systems, they may also be common drivers of inward comet delivery. The same gravitational dynamics that in our system occasionally send outer solar system objects falling inward would operate in other systems. Other planetary systems might be receiving regular deliveries of chemically complex material from their outer regions. For the question of life elsewhere in the universe, this matters. If the delivery of organic precursors from outer to inner solar system regions is a standard process driven by a common structural feature of planetary systems, then the chemical prerequisites for life might be standard too. Not special, not rare, routine. This does not mean life is common. There are many steps between having the right molecules and having biology, but it means the first step may be far easier and far more widespread than previously appreciated. Webb is giving us a new lens for reading our own solar system, and what we read there is beginning to inform how we expect other systems to look: more organized than expected at their edges, more chemically active, more structurally complex. The universe, seen through Webb's infrared eye, is richer and stranger than the visible universe alone ever revealed. Science is a profession as well as a method. Scientists have careers, reputations, funding to maintain, and peer relationships to preserve. These pressures shape what questions get asked publicly and how carefully those questions are worded. Some questions are avoided, not because they are scientifically unreasonable, but because stating them openly carries professional risk. There is a question circulating quietly in the planetary science community right now that fits this description. It is not the question of whether Planet 9 exists. That question is already in the open, published, debated, funded. It carries professional risk for the researchers who champion it, but it is scientifically mainstream enough to survive. The quieter question is about the chemical findings. Specifically, it is this: given the complexity of the organic chemistry Webb has detected in the outer solar system, given the presence of possible nuclear-based precursors in a region where they should not form under standard models, given the apparent role of a large gravitational body in accelerating that chemistry, is it possible that some of what we are seeing is the product of chemistry that has progressed further than we have a theoretical framework to account for? No serious scientist is publicly suggesting that there is life in the outer solar system. That would require extraordinary evidence that does not yet exist. But a smaller and more defensible version of the question is being asked in seminar rooms and at conference dinners rather than in published papers. If the chemistry at the edge of our solar system is more advanced than our models predict, is our model of what spontaneous chemistry can achieve in cold, high radiation, gravitationally active environments simply incomplete? This is not a question about life. It is a question about chemistry, about whether we fully understand the upper limit of what abiotic, meaning non-biological, chemistry can produce under conditions that exist in nature, but that we cannot fully replicate in laboratories. The distinction matters because the answer changes how we should interpret the organic molecules Webb found. If our model of cold space abiotic chemistry is complete and those molecules still exceed it, we have a mystery that needs an explanation. If the model is incomplete and those molecules fall within an expanded understanding of what chemistry can do, we have a scientific opportunity to expand the model. Most researchers lean toward the second interpretation. Cold space chemistry is poorly understood because it is extraordinarily difficult to study under controlled conditions. The environments involved, near absolute zero temperatures, high vacuum conditions, cosmic ray fluxes measured over millions of years, are not reproducible in any laboratory on Earth. Webb is giving us a window into what happens in those environments over geological time. What it is showing is that the chemistry goes further than the models predicted. The question scientists are reluctant to answer out loud is simply this: where does chemistry end and something more complex begin, and are we certain we know the difference at the edges? Webb's data is making that question harder to avoid, and what you are about to hear next may be the most important part of this entire story. This is the frontier that Webb has opened. Not just a new object, not just a new orbit, a new question about the limits of what chemistry can do in the cold and the dark over billions of years. The answer, when it comes, will reshape astrobiology, planetary science, and our understanding of how common the building blocks of life really are in the universe. The final chapter of this journey is the one that brings it all together. Science does not stop at a discovery. It accelerates through one. Every finding Webb has made in the outer solar system, the anomalous cluster, the large dark object, the crystalline ice, the organic signatures, the statistical evidence for an unseen massive body. Each of these is simultaneously a conclusion and a starting point, a door that opens into a room full of more doors. The next decade of outer solar system science has a roadmap built from Webb's contributions and the questions those contributions have generated. The most immediate priority is the confirmation or elimination of the Planet 9 candidates Webb identified. This requires follow-up observations spaced months apart to track candidate objects precisely enough to determine whether they are solar system bodies or distant background objects. Several programs are underway. A definitive answer is expected within a few years. If any candidate is confirmed as a large solar system body, the response will be immediate and comprehensive. Observing campaigns will shift to characterize the object's size, mass, surface properties, and orbital parameters in as much detail as possible. Mission planners at space agencies around the world will begin preliminary work on what a flyby or orbiter might look like, knowing any such mission would take decades to arrive. If no candidate is confirmed, the search continues. Webb's survey is not complete. The high probability zones are large, and systematic coverage takes time. The Vera Rubin Observatory, designed for deep, wide-field optical surveys, will soon begin operations and will search for faint reflected light that complements Webb's infrared detection. The chemical findings will be followed up with dedicated spectroscopic programs. More objects, more data, better signal on the molecular signatures tentatively identified. The question of whether nuclear-based precursors are genuinely present in outer solar system surface chemistry will be addressed in the coming years. Mission planning is already shifting in response to Webb's findings. The concept of a dedicated outer solar system probe has gained traction in recent mission concept studies. Such a mission would take decades to reach its targets, but planning must begin now for it to become reality within the careers of researchers currently in school today. For everyone following this story, what matters most is simple. The edge of our solar system is not what we thought it was. It is not empty. It is not quiet. It is not finished being remarkable. Webb has shown us that the region once considered a frozen graveyard is chemically active, structurally organized, and shaped by at least one object we have not yet confirmed, but can no longer ignore. It has shown us that the ingredients pointing toward life exist not just in warm, star-adjacent zones, but at the cold, dark, gravitationally complex edges of solar systems. It is placed in front of us, at the very edge of everything our star has ever touched, a question as old as the first human who looked up at the night sky. What is really out there? Webb is finally giving us the tools to begin answering it. The next few years will be decisive. Confirmation or a deeper question. Either outcome advances the science. Either outcome pushes humanity's understanding of the solar system further than it has ever been. The edge is not the end. It never was. It is where the most important questions are waiting. And for the first time, we have a telescope powerful enough to ask them properly.